So this is continuation, chapter 5. And so what I want to talk about in this video is enthalpy. So I kind of alluded it to you in the previous video when we were doing the calculation here. So delta H is what we call a constant for any substance. So this is what we call enthalpy, delta H, okay? And delta H is what we call a state function. It is independent of path. It is independent of path. So what exactly does that mean? Well, some books describe it as if you are climbing a mountain, okay, these are my mountains, not very nice mountains. If I were to go straight up that mountain, or if I were to zigzag up to the top of the mountain, it really does not matter how I get to the top. Okay, so enthalpy means all I care about is the final state minus the initial state. Okay, we're always looking at change. What are things that are not state functions? Well, those are going to be heat, Q, and W. Okay, so lowercase letters in thermochemistry always mean non-state functions. Capital letters mean state functions. So these are not state functions. All that means, and it's exactly what the example we were just doing, okay? Q is going to change depending upon how much stuff I put in there, the amount of water, so on and so forth. But the delta H of the overall is going to stay the same, okay? So my definition of enthalpy is related to energy and PV, okay? So I could change that expression to have my deltas here, because what we care about is the change. We don't care about anything else. But we know that most of our experiments are under what we call constant pressure, meaning we're in a lab setting and we have it open to the surroundings. I'm not changing the pressure. So really the definition of enthalpy is this, okay? So delta H is equal to delta E plus P delta V. Well, we know P delta V, okay, is kind of my definition of work, okay? Work is equal to negative P delta V. So if I were to take E, Q plus W, that's the value of E, and then I take my P delta V and make it negative because the definition is negative P delta V, I then have this relationship, okay? So at constant pressure, QP is equal to the enthalpy of the reaction. So this is why in first year chemistry, we interchange these two. We kind of said, okay, here's delta H, here's Q, and you kind of use them the same way. Now, the only thing I want to mention at this point, and then we'll move on to this is where, if you remember, we called things exo or endo depending upon the sign of the delta H. So if the sign was negative, we called that exothermic. If the sign was positive, we called that an endothermic process. So back when we were doing this, okay, we were not involving delta E, because delta E really only plays in if you happen to have a gas. So if I have a gas, I do have an equation that we're going to see much more thoroughly later on, but we're going to use it kind of as a tool rather than the calculation. It's called the ideal gas law. And the ideal gas law is pressure times volume of a gas is equal to the number of moles times a constant times the temperature of that gas, okay? So we are going to substitute in, if we were to take this equation and put the P delta V over on this side and just have E, that would be how it looks. I'm going to substitute P and V for nRT. Okay, why I'm going to do that is because I could easily look at what I call the number of moles of gas. So this is moles of gas in the equation, okay? And this is only for gases will this apply to. So what we're going to really explore here is not the calculation itself, but what is the relationship between delta E and delta H? So what I'm going to have you do in these next two problems is figure out, okay, is delta E the same as delta H? Is delta E greater than delta H? And is delta E less than delta H? Okay, so I'm going to show you two examples of what I mean by this. So if I have a mole of ice is melting at 0 degrees Celsius at a constant pressure of 1 atmosphere, 1440 calories are absorbed by the system. Molar volumes are 0.0196 and 0.018 liters respectively. Okay, so again, back to this ideal gas law, we used to focus on the calculation. Instead, we're just going to focus on what the relationship is. We are still going to look and use that equation, but we're not going to focus too much more on the math. So if I take water in the solid form and convert it to water in the liquid form, okay, I am applying heat, okay? So heat in this instance happens to be on the reactant side. If it's on the reactant side, this is an endothermic process. Well, do I have any gases in this equation? No. So my delta N happens to be 0. Well, if I go back to this equation, if my delta N is 0, everything here is going to be 0. So what's my relationship? Well, my delta E is going to be the same as my delta H. So that's why in first year chemistry, we really didn't focus too much on delta E, because if you don't have a gas being produced, you really have no difference between the two, okay? You could kind of see how it plays in. But to the second example here, if you do have a production of a gas, then you have to account for that. So I have a thermal decomposition of magnesium carbonate. Here's my delta H at so many Kelvin and 1 atmosphere pressure. Again, if we were doing the math, we need all of this information. Molar volume of magnesium carbonate is 0.028 liters. Magnesium oxide is 0.011 liters. What is the relationship between delta H and delta E? So again, I am not expecting you to know this equation. Okay, so this is just for note-taking reasons. There used to be much more emphasis on the AP test about the actual chemical reactions. So you produce carbon dioxide. Anytime you heat a carbonate, by the way, you produce carbon dioxide. So heat is on the left-hand side. This is an endothermic process, okay? We also know that because the delta H given in this problem is a positive quantity. Okay, so anytime delta H is positive, we know it is endothermic, and the heat's going to be on the left-hand side. Exothermic, heat's over on the product side. The delta H is going to be negative. So the only gas I have here is CO2, okay? And the delta N is always going to be products minus reactants. So all of our deltas, except for one, are always products minus reactants. We're always looking at the end versus the beginning. So my delta N is going to be 1 minus 0. So that means my change in N is going to be 1. So if I take my delta E is equal to delta H minus delta N RT, okay, I am given that my delta H is positive. It's 26,000 calories, okay? But what I care about is it's a positive quantity. And I know my N is 1 times R times T. Okay, again, not focusing too much on the calculation, but if you wanted to know, it comes out to be around 300-ish, okay? And this is in calories. So in terms of magnitude, not sign, because sign will make it very wishy-washy. 26,000 minus 300, this number is going to be smaller, the delta E. So the delta E here is not going to be equal to delta H, okay? It's going to be magnitude-wise smaller because you're going to be subtracting away some quantity, okay? And that's the reasoning I want you to do. I don't want us to focus on the calculation. I want you to focus on the reasoning. So let's say I had this, and let's say this was exothermic. So let's say the delta H was negative. Okay, and then I was subtracting the quantity of the delta N because that's part of the equation. It's a minus delta N. Okay, so if I have a positive change in gas, what's going to happen? Well, the delta E magnitude-wise is going to end up greater than the delta H. So that's the reasoning part here. Again, what if the delta N was negative? Well, then this becomes a positive quantity. Well, that would make delta E bigger for endothermics, but not for exothermics. So that's going to be kind of the process I want you to go with on these types of problems. Again, not emphasizing the numbers. The numbers are helpful just to see them, but we're not going to be doing any calculations. Instead, I want you to just understand the relationship.